Hi, I'm Kyle Likov and today I'm going to discuss problem 6.2-3. The problem states ammonia gas is diffusing through nitrogen gas in steady state conditions with N2 non-diffusing since it is insoluble in one boundary. The total pressure is 1.013 times 10 raised to the power 5 Pascal and the temperature is 208 Kelvin. The partial pressure of ammonia at one point is 1.33 times 10 raised to the power 4 Pascal and at the other point 20 millimeters away, it is 6.666 times 10 raised to the power 3 pascals. The diffusivity coefficient for A diffusing into B for the mixture at 1.013 times 10 raised to the power 5 pascal and 298 Kelvin is 2.30 times 10 raised to the power of 5 negative 5 meters squared per second. Calculate the flux of ammonia in kilogram mole per second meter squared and do the same as A, but assume that nitrogen gas also diffuses. That is, both boundaries are permeable to both gases, and the flux is equimolar counter diffusion, in which case is greater. So we are given with the total pressure of 1.013 times 10 raised to the power 5 Pascal and the partial pressures at point A. Ay, partial pressure of A at point 1 and point 2, which is 1.33 times 10 raised to the power 4 Pascal and 6.666 times 10 raised to the power 3 Pascals respectively. And the distance of diffusion is 20 millimeters, which is also equal to 0.020 meters. And our temperature is 288 Kelvin, and the diffusivity coefficient of A for A diffusing into B is 2.30 times 10 raised to the power of negative 5 meters squared per second. So we are required to calculate the flux of ammonia in kilogram mole per second meter squared. And do the same as A, but assume that N2 also diffuses. That is, both boundaries are permeable to both gases and the flux is equimolar counter diffusion, in which case is greater. So before we go to our solution, we need to set our assumptions first. Steady state conditions, one-dimensional mass transfer, and no chemical reaction. So to solve for diffusion of ammonia through non-diffusing nitrogen gas, our working equation is equation 6.2-22 engine please, which is flux is equal to diffusivity coefficient for A diffusing into B times the total pressure all over gas constant times temperature times the distance of diffusion times the log mean value of pressure B times the quantity of the partial pressure of A at point 1 minus partial pressure of A at point 2. Since we don't have the log mean pressure of B, we can use equation 6.2-21. So 6.2-21 is one log mean of pressure B, which is equal to PB2 minus PB1 all over Ln times the quantity of PB2 minus PB1, which is also equal to PA1 minus PA2 all over Ln times P minus PA2 over P minus PA1. So solving for PB1 and PB2, PB1 is just equal to P minus partial pressure of A at point 1. So we get a value of PB1 of 8.797 times 10 raised to the power of 4 Pascal. And for PB2, we get a value of 9.463 times 10 raised to the power of 4 Pascal. And substituting the obtained values in equation 6.2-21, we got a value of ppm with 9.126 times 10 raised to the power of 4 pascals. And we substitute the value of ppm in equation 6.2-22, which is our working equation. We get a value of flux with 3.434 times 10 raised to the power of 6 kilomoles per second meter squared. To calculate for flux in equimolar counter diffusion, we can use equation 6.1-13 engine please. So flux is equal to JAZ is equal to DAB times TA1 minus TA2 all over RT times Z2 minus Z1. Plugging in all the values, we got a flux of 3.093 times 10 raised to the power of 6 kilomoles per second meter squared. Therefore, the flux is greater than AC.
Hello everyone, I am Alfred Albacete. Today I will present the solution to problem 6.2-4. The problem is about the diffusion of methane through a non-diffusing helium. And the problem states that a methane gas is diffusing in a straight tube 0.1 meters long containing helium at 298 Kelvin and a total pressure of 1.01325 times 10 raised to 5 Pascal. The partial pressure of methane is 1.4 times 10 raised to 4 Pascal at one end and 1.333 times 10 to the power of 3 Pascal at the other end. Helium is insoluble in one boundary and hence is non-diffusing or stagnant. The diffusivity is given in table 6.2-1. Calculate the flux of methane in kilograms mole per meter squared second at steady state. In this problem, we are given with Z, the length of the tube at 0.1 meters, the total pressure at 1.01325 times 10 to the power of 5 Pascal, the partial pressure at point 1 equal to 1.4 times 10 to the power of 4 Pascal, partial pressure at point 2 equal to 1.333 times 10 to the power of 3 Pascal, and the temperature at 298 Kelvin. We are required to solve for the flux of methane in kilogram mole per meter squared seconds. The first assumption for this problem is that it is on steady state conditions, one-dimensional mass transfer in the Z direction, and finally, there is no chemical reaction. On the top right is the diagram for the problem. For the case of A diffusing through a non-diffusing B, the flux of A is equal to the diffusivity coefficient multiplied with the total pressure over the gas constant multiplied with the temperature times Z2 minus Z1 times the natural log of the total pressure minus the partial pressure at point 2 over the total pressure minus partial pressure at point 1, where R is equal to 8.314 times 10 to the power of 3 Pascal meter squared over kilogram moles Kelvin. And from table 6.2-1, for helium and methane at 298 Kelvin, we are able to find the value for the diffusivity, which is 0.675 times 10 to the negative 4 meters squared per second. Finally, plugging in values into the equation to solve for the flux, we get the value for the flux of methane equal to 3.74 times 10 to the negative 6 kilogram mole per meter squared seconds.
Hi, I'm Harvey J. Tiang and I will discuss problem 6.2-5 of the basic principles of mass transfer. The problem is, mass transfer is occurring from a sphere of naphthalene having a radius of 10 mm. The sphere is in a large volume of still air at 52.6 degrees Celsius and 1 atm absolute pressure. The vapor pressure of naphthalene at 52.6 degrees Celsius is 1 mmHg. The diffusivity of naphthalene in air at 0 degrees Celsius is 5.16 times 10 raised to negative 6 meters squared per second. Calculate the rate of evaporation of naphthalene from the surface in kilogram mole per second meter squared. This problem is a special case for A, which is the naphthalene diffusing through stagnant non-diffusing B, which is the air. So our assumption would be it would be a steady state, no chemical reaction, and one-dimensional mass transfer. So the given is the vapor pressure of naphthalene at 52.6 degrees Celsius is given by 1 mmHg converted to atm to be 1.316 times 10 to the power of negative 3. Then the vapor pressure of naphthalene at point 2, which is pure air, is equal to 0 atm. The temperature is given by 52.6 converted to Kelvin to be 325.6. The surrounding pressure is given as 1 atm converted to Pascal to be 1.0132 times 10 to the power of 5. The diffusivity of naphthalene at 0 degrees Celsius is given as 5.16 times 10 raised to negative 6. The radius of the naphthalene sphere is 10 mm converted to meter to become 0.010 meters. The required is the rate of evaporation, denoted as N sub A1, or the total flux. The solution, the first step would be get log mean value of pressure B using equation 6.2-21, where the log mean pressure of B, or the air, is equal to the pressure of B at point 2 minus the pressure of B at point 1 over Ln, the pressure of B of point 2 over the pressure of B at point 1, where the pressure of B at point 2 is just equal to the surrounding pressure P minus the vapor pressure of naphthalene at point 2, which is on the pure air, which gives us a value of 1 atm. For the pressure of B at the surface, or at the point 1, it is given by the surrounding pressure minus the vapor pressure of naphthalene at the surface, which gives us, substituting, which gives us a value of 0.9987 atm. Substituting the value of the pressure of point B at point 2 and the pressure of point B at 1 gives us the log mean pressure to be 0.993 atm. For step 2, we correct the diffusivity of naphthalene at 0 degrees Celsius using Fuller et al. Equation, which is equation 6.2-45. So the formula would be the corrected diffusivity value is equal to the diffusivity value at that temperature times the temperature you want it to be corrected over the temperature it is given raised to 1.75. Substituting the values, we get the new diffusivity value at 325.6 Kelvin to be 7.021 times 10 raised to negative 6. The next step, or the last step, is to solve for the rate of evaporation of naphthalene in the surface using equation 6.2-22. So the formula of the rate of evaporation is just equal to the diffusivity, the corrected diffusivity, times the surrounding pressure, times the difference of the vapor pressure of A at point 1 minus the vapor pressure of A at point 2, over the real gas constant times the temperature times the radius of the sphere times the log mean pressure of B. Substituting the values into our formula, we get that the value of the rate of evaporation of naphthalene in the surface is equal to 3.46 times 10 raised to negative 8 kilogram mole per second meter squared.
Good day everyone, I am Oliver Mangusing and I will present the solution to problem 6.2-8. The problem states that water at 25 degrees Celsius is flowing in a covered irrigation ditch below ground. Every 100 feet, there is a vent line 1 inch inside diameter and 1 foot long to the outside atmosphere at 25 degrees Celsius. There are 10 vents in the 1,000 foot ditch. The outside air can be assumed dry. Calculate the total evaporation loss in pound mass per day. Assume that the partial pressure of water vapor at the surface of the water is the vapor pressure 23.76 millimeters of mercury at 25 degrees Celsius. Use the diffusivity from table 6.2-1. In this problem, we are given that water, denoted as A, at 25 degrees Celsius flows along a ditch 1,000 feet long. Along the ditch are 10 vents spaced evenly at 100 feet. Each of the vents are 1 foot long with an internal diameter of 1 inch. We have dry air, denoted as B, outside the vents at 25 degrees Celsius. We denote point 1 at the surface of the water and point 2 just outside the vent. We also assume an axis Z whose direction is given by this arrow. We are also given that the partial pressure of water at point 1 is 23.76 millimeters of mercury. We are required to find the evaporation loss of water in pound mass per day. For the solution, we assume steady state and one-dimensional mass transfer. We also assume that there are no chemical reactions. After this, from the figure and from the assumptions, we have a temperature of 25 degrees Celsius and a Z2 minus Z1 at 1 foot. Since the air is dry, the partial pressure of water at point 2 is 0. From our assumption, the pressure is 1 atmosphere. The diameter of the vent is 1 inch and there are 10 vents. Using table 6.2-1 from John Copley's 1993, for water and air at 25 degrees Celsius, the diffusivity is 0.260 times 10 to the negative 4 square meters per second. In this problem, the air cannot diffuse into the water. Thus, we use equation 6.2-20 from John Copley's 1993. Also, we first base our computations on one vent, as all the vents are identical. Plugging in values into the previous equation, we have a mass flux of 1.107 times 10 to the negative 4 mole per square meter second. Now, we solve for the area of diffusion, which is the cross-sectional area of the vent pi d squared divided by 4. Plugging in the value for d, we have the area of 5.067 times 10 to the negative 4 square meters. We note that this area is for one vent only. Once we have the mass flux and the area, we can now solve for the molar flow rate of water using equation 6.2-28 from John Copley's 1993. Plugging in the mass flux and the area, we have a molar flow rate of 5.61 times 10 to the negative 8 mole per second. We then convert the unit mole per second to pound mass per day, as these are the units required. We use the molar mass of water at 18 grams per mole, conversion factor for gram to pound mass, and conversion factor for second to day. Finally, we have the mass flow rate at 1.92 times 10 to the negative 4 pound mass per day. We note that this is for one vent only. For 10 vents, we multiply the previous result by 10. Thus, we get the evaporation loss of water from 10 vents at 1.92 times 10 to the negative 3 pound mass of H2O per day. That would be all, and thank you.